So if you are interested in more details, then you may find them in the famous textbook by Christine's book. So the setting is the following. So we assume that we are given three spaces, and they are smooth varieties. And they have action of an reductive group G, smooth G varieties. And we consider G12, this is a subvariety of the product M1 times M2, and also consider Z of Q3. This is so they are closed to G subvarieties. And we define the composition of D12 and D23 to be the something like this. So this is this Pij here is a natural projection from a triple product to product of Mi and Mj. So this is projection. And we assume that projection P13 restricted to this intersection. So this is surjection to this composition. And we assume that this is proper. Okay, so they are assumptions. And under these assumptions, we can define. So we have a well-defined, well-defined RG bilinear operation. Which is called convolution. So this is from equivalent K of G12 times equivalent K of D23 to equivalent K of the composition B12, D23. And so this is operation will be denoted by star, and star of F and G. So this is given by, so first we pull back F along this projection 1, 2, and also we consider the pull back of G along this projection 2, 3, and take up derived tensor product on the smooth ambient space. So this triple product. So note that. So we are working on a bounded derived category of equivalent coherent waves. So to make this tensor product closed on inside bounded derived category, we need to to define this tensor product, we need to find the resolution of one of factors, but to take and we need to find finite length resolution. So to make sure to get finite length resolution, we need to work on this smooth ambient space, and we push. So this is more precise. This is derived push forward, but anyway, so by this we can define convolution. Okay, so the important thing is that this operation does depend on this ambient space. Okay. And so in our example here, so we considered this Nakajima's graded quiver variety. So there are two versions, smooth and affine, and we have proper map pi, and ZW is defined to be a fiber product of this MW, and then we find that the composition of ZW with itself is again ZW. So in particular, by this convolution, so this is an algebra. So this is convolution algebra. And this L is defined to be the fiber of origin. And from definition, so we find that the composition of ZW and LW is same as LW. So this space is a module by convolution. Okay. So this is complement for what I explained yesterday. And also I have one more thing. So we can construct a deformed Weyl module by this convolution construction. And also we can construct a tensor product of deformed Weyl module. So I explain how to construct tensor product by this equivalence theory. So we took this W, this is I graded vector space, and we take any decomposition of this I graded vector. So this is decomposition of I graded vector space. So each factor is, again, I had graded. And according to this, the composition, we define a one parameter subgroup of GW. So this is, I will denote this by chi. And chi of T is defined to be a by this formula. So T, non-zero scalar T, acts on the case factor by this case power of T. Okay, and then we define So we have graded quiver variety. So we define closed subgroup, subvariety of this. So it is denoted by T0. This. So this will be the space of points in M0, which is attracted to the origin. So if we consider the limit t to 0 of this chi t times x, then this will be 0. So this is closed subvariety of this M0. And we take its pre-image along this pi to define this t inside this M. And so we defined two subvarieties, and they are no longer stable under this GW action, but they are stable under the product of GW. So they act here and here. So we can consider the following equivalent case theory. So we consider equivalent case theory of this T, but the group of equivariance is now the product of. So now we consider K of GW1 times. So we consider this kind of equivalent case theory and take completion. Then, and this is theorem by again Nakajima. Then this will be isomorphic to the product of equivalent K. And this isomorphism can be seen as modules of a quantum loop algebra. So by using this algebra homomorphism, we can regard left-hand side and right-hand side as left-hand side as a UQ-LG module. And as a UQ-LG module, this is equal to this module. So as an example of this construction, so we can see the following thing. So let us assume that our lambda here is a sum of fundamental ones. So I1, I1 P1 plus IN Pn. And we have the corresponding graded vector space W, and we try to decompose this W into one-dimensional pieces according to this sum. So and we assume that this integer P1 to Pn is decreasing. So in this case, actually, so if we consider the sorry, so we take maximal torus inside this GW and consider the equivalent T equivalent case theory of corresponding subvariety T of sorry. So we just consider whole M. No, so sorry, whole L here. Okay. Then so this is actually equal to the tensor product of deformed fundamental modules in this order. And we consider the whole variety M instead of L. So this is actually equal to the opposite order tensor product. So this is product of fundamental ones. But now the order of tensor product is opposite. Phi of I1 here. Like this, we get this construction. So this is because so in this extremal case, so L will be the special case of this T, and the whole variety M is also the special case of this T. So in this case there is only single point in T0. So this is just origin. And for the second case, so everything is attracted to this 0. So this T will be this whole M. Sorry? T0 is yes, affine subvariety, affine closed subvariety. So this is affine subvariety, and this is closed subvariety of affine space. So it's affine. Okay. So this is the experimental case, and from this equation we get the tensor. So if we forget about this equivalence, then we get to the local one module is actually a product of fundamental ones in this ordering. For example. Okay. And next I will explain about the relationship between this graded quiver variety to the derived category of Dinting quivers. So this is the next topic. Relation to DQ. So DQ is a symbol for the derived category of representation of Q, and Q is a Dinting quiver. Okay, so first let us recall the fundamental theorem due to Gabriel. About the classification of indecomposable object in this category. So he found a bijection between the indecomposable object in this category of representation in Q with a set of positive roots. And this correspondence is given by just taking the dimension vector of representation. So if we have indecomposable Q representation, then this is I-graded. So we have an underlying I-graded vector space like this. So Mi. So we just take the dimension vector. So take a sum of so this kind of linear combination we consider. Then we get positive root, and this correspondence gives a bijection between isomorphism classes and positive roots. So in particular, if we are given a positive root here, then we have corresponding indecomposable representation, and I will denote it by M alpha. So for example, in type A2 case, and let us take Q to be this quiver. So this is the infinite diagram of type A2, and we consider this orientation. So this is first one. Then so the set of positive roots consists of 3 positive roots. So we have alpha 1, alpha 2, and alpha 1 plus alpha 2. And so as indecomposable representation, we can take, for example, so something like this. So this is indecomposable representation whose dimension vector is alpha 2. And also we have this representation. This is indecomposable for alpha 1. Actually, they are simple representations. And the other indecomposable representation is something like this. And this is indecomposable representation attached to alpha 1 plus alpha 2. And we have, for example, this kind of exact sequence. Okay, so we have 3 indecomposables, and they are correspond to positive. This is example. Sorry, wait. Sorry, wait. So this theorem only about, so we only consider roots, not weights. And so let us consider the following quiver. So consider a quiver delta. So whose vertex set delta 0 is I hat. So I hat is something I defined yesterday. So this is set of pairs of dt index and integer, and P has the same parity as our fixed parity function, and arrow set delta 1 is given by sorry. So we have for any vertex IP, so we have an arrow to JP plus 1 if J is adjacent to I in Vinci diagram. So this is infinite quiver, but very, very simple quiver. So in an example, so in again in type A2, so the set I hat is given by, so this is I direction, and we have the so this is vertex set for this quiver. So this is the direction, and the arrows are so something like this. So we consider this kind of zigzag arrows. Yes. So this is delta. So this is delta. And this simple quiver actually describes the structure of derived category of representations in quiver. So this is a theorem due to Happel. So he constructed an quiver isomorphism between this quiver delta and so-called Auslander writing quiver of derived category of rep2. So this depends on the choice of our orientations, and so this isomorphism, so particularly in this is a bijection between vertex set. So vertex set is I hat. So this is in bijection with the set of vertex set of this Auslander writing quiver. And by definition, the vertex set of Auslander writing quiver is given by the set of isomorphism classes of indecomposable object in this category D2. And indecomposable objects of category D2 is given by the shift of indecomposable module. So alpha is from alpha is positive root and k is an integer. So in other words, this is a complex of representations whose cohomology is non-trivial only at minus k degree. So we have this bijection, and by definition, the arrows for Auslander writing quiver corresponds to the so arrows in this Auslander writing quiver. This represent so-called irreducible morphisms. So irreducible means that there is no non-trivial decomposition of morphism. So we cannot express this irreducible morphism as a composition of other non-trivial morphisms. So for example, so in this example in type A2, the arrow here and here, they are irreducible morphisms. Yes?
The relation of Q and delta.
Q and delta?
When you are given quiver Q,
Yes.
you can make quiver delta. But it seems that
this quiver doesn't depend on any choice of Q. So this is only depends on our choice of real algebra, AD type real algebra. So this doesn't depend on the choice of Q, but this isomorphism depends on the choice of Q. The delta. Yes, I will explain in example. So yes, epsilon ice, yes.
But again, given Q,
Yes.
there is new information about Q.
So epsilon epsilon doesn't depend on the choice of orientation. So the data doesn't depend on any choice of orientation, but this isomorphism depends. So in this example, so with this orientation, for example, so we have the following thing. So we have this exact sequence can be embedded into as a subquiver of this. So here we have M of alpha 2, and here we have M of alpha 1, and here we have M of alpha 1 plus alpha 2. And these arrows represent these irreducible morphisms. And this is a part, so this is a part corresponding to the lip Q. So this is the heart of standard structure. But here, so we have M alpha 2 of, so 1/5 of M alpha 2. And here we have M alpha 1 plus alpha 2 of, so shifted by 1 here. And M alpha 1 of shifted by 1. So we find here the left Q. And we find here the left Q shifted by 1. Or something like this. And again, so here we have M alpha 1 shifted by -1. -1. -1. Yes, so this is, yes, this statement is only for finite type. So for non-finite type, we have a generalization due to Katz theorem, but that is not a bijection. Okay, so this is the what this theorem says. So happen. Yes. Yes, that is the assumption. And I forgot to mention that this quiver isomorphism is unique up to shift. Unique up to shift. Up to G shift. I forgot one. And actually, this derived category of Lynching quiver is related to the structure of graded quiver variety. And to describe it, I need one more quiver. So we consider another quiver. Gamma, such that the arrow set is the same as before. So arrow set, vertex set is the same as I had. And arrow set gamma 1 is given by the following rule. So the number of arrows from x to y is given by the dimension of x to 1 in the derived category of Lynching quiver from h to x to h to y. So this extension in derived category is, so this is simply defined by, so this is the same as the Hom in this derived category, x, y, shifted by 1. Okay, so this is definition of x1 in derived category. And we consider this quiver. So this is a kind. So this is maybe x1 quiver of derived category. So let me show this in this example. So in this example, so this is quiver delta, but we consider another quiver with same vertex set, but the arrows are given by x to 1. So for example, so this exact sequence, short exact sequence represent extension x to 1 from m alpha 2 to m alpha 1. Maybe opposite. Sorry, m alpha 1 to m alpha 2. So we have an arrow from m alpha 1 to m alpha 2. Like this in x quiver. So and by symmetry we get these horizontal arrows in this and we also find x to 1 from m1 shifted by 0 to m alpha 1 shifted by 1. Sorry, maybe opposite. Yeah, opposite, sorry. So from here to here, we have an x to 1 in derived category. And by symmetry, we have these arrows. So like this. And also we have, yeah. So from here to here, we also have x to 1. So this is the quiver gamma for type A2. So this is more complicated than the quiver delta. And this number, I will denote this by d of xy. And actually, this number doesn't depend on, this doesn't depend on our choice of Q. Because for different choice of orientation, we have an equivalence of derived category by using so-called reflection factors. So this number doesn't change under reflection factor. So So this number is independent of the choice of orientation. Yes?
Still confusing that isomorphism will explain exact correspondence between I comma keys in the left hand side and MAK on the right hand side.
Right hand side. So yeah, this isomorphism that depends on the choice of Q. So to describe this, so we have to take so-called height function. So this is a integer varied function satisfying this condition. So if there is an arrow in our orientation from I to j, then I is bigger than j by 1. So we then this HQ determined by this this rule. So I psi I. So this is given by the II of 0. So this II is an indecomposable envelope. Injective envelope of simple representation associated with I. So this is a unique indecomposable injective object which has M alpha I as a submodule. And other representation can be obtained from this injective envelope by applying so-called Auslander-Leiten translation. And the Auslander-Leiten translation is given by the shift by 2 or minus 2 in this diagram. So this is precise correspondence. So okay. So it does depend on choice of this height function, and this height function is unique up to shift from our choice of orientation. And the relation to graded quiver variety, this is given by Keller and Scherotzke. This is 2016. So this said that so we have a fine graded quiver variety MW, and they identify this affine variety as a variety of representations of certain algebra, which is obtained from our X1 quiver with relation. Okay, and the important thing is that so by definition, this space of representation of this algebra is a affine closed subvariety of the space of representation of X1 quiver, and this representation of X1 quiver is just given by the direct sum of home spaces from WX to WY, and here we have multiplicity dxy. So in particular, this theorem gives an affine embedding of this affine variety into an affine space. So this is just an affine space. And they also, and for this relation, so this relation is given by the linear combination of passes in this quiver gamma of length greater than 1. Linear combinations of, and they also prove that the number of relations from x to y is given by a dimension of x to 2. Of corresponding indecomposable objects in the derived category. So this is a theorem due to Keller Scherotzke. So,
Excuse me?
yes.
I can understand a little bit. So on the right-hand side, rep W gamma, that's the vector space,
Yes.
right? And then on the left-hand side, it's affine.
Yes. Affine variety.
Right.
Yes.
And in the middle, like my question is, does the middle say something about kind of how curvy the affine variety is, or is it kind of
So this is so let me show this in example. So yes.
the middle isn't also a vector space, or
So this is a closed subvariety. This is closed subvariety of this affine space, and the defining equation for this closed subvariety is given by this relation. So
linear?
not a linear relation. So for example, so in this example, the relations are given by, so we have three kinds of arrows. So we denote this horizontal arrow by A, and we denote by this oblique arrows by B and C. Yeah, sorry. This is B, and this arrow will be C. Then the relation are given by, for example, so we have relation like AB is equal to BA, and CA is equal to AC, and cube of A is equal to BC. So this says that so if we take this length 2 path, then this path is equal to this path. So for this square, this square is a commutative square or something like that. And for this last equation, we have the cube of A. So this is starting from this to this, and from this to this, we have another length 2 path, which is BC. So this kind of path. Okay. And yes, so this is relation, and so this is a locus which this relation vanishes. So this is called subvariety. And sorry, I forgot to mention that this is also GW equivalent. So this is isomorphism of GW varieties. So here we also have the natural conjugation action of GW, and so this is the very nice description of graded quiver variety. And we can use this theorem to analyze the singularity of R-matrix. So I will explain this. So finally, so this talk. Okay, so we have an application. To singularity of so-called R matrix. So first I need to explain what is R matrix in this context. So for any finite dimensional representation of quantum loop algebra, we can define its formal spectral parameter shift denoted by V of V of Z. So this is we just take tensor product with this field of rational functions in formal parameter Z, and so this is naturally UQ module. So we just forget about this part, but we can apply the spectral parameter shift by Z. So this is formal spectral parameter shift. So this is the finite dimensional modules of a quantum loop algebra. So simply, yes. So this is formal spectral parameters. And so in the beginning of the talk yesterday, I said that if we take so this category C is non-commutative, I said. Tau Z is a spectral parameter shift. So this is so actually this is so in this case, so this has an action of this algebra base change, and this is an automorphism of this algebra, and we consider pullback of this module under this automorphism. Okay. And so if we take two irreducible representation, for example, then the tensor product of the two, so this does depends on the choice of ordering. So they are not always isomorphic. So it happened that they are not isomorphic. But if we apply formal spectral parameter shift for these modules, then we always get an isomorphism. And this isomorphism is the so-called R-matrix. So there is an isomorphism. And if we normalize, so because irreducible representation are highest weight representation, so we can take highest weight vectors. So this is highest weight vectors. Then we import this normalization. So this R sends highest weight vector to highest weight vector. So under this normalization, this isomorphism is determined uniquely. So this is called the normalized R matrix. And this is an matrix valued rational function. So this rationally depends on the ratios of spectral parameters. And by using normalized R matrix, we can define the numerical invariant for pair of representations, which is a polar order of R matrix. at this ratio of spectral component at 1. So we can consider this. So this is by definition non-negative integer. And this numerical invariant is very important to study the tensor product structure of representations. So for example, we have the following theorem. So this is due to Kahn-Schwarz-Timo. So we need to assume that some condition which said that to assume one of V1, V2 is so-called real module. So real means that tensor square is again simple. And for example, fundamental modules are known to be real. So this is some assumption, but under this assumption, so we have the following statement are mutually equivalent. So the tensor product of V1 and V2 is again irreducible. And second condition is that the commutativity of tensor product. So the final condition is that the order of R matrix are 0. So under this third condition, so there is no singularity at 1. So for this R matrix, so we can specialize that R matrix. So and to obtain this isomorphism, for example. So from this theorem, we can say that this numerical invariant, so for order of R matrix, from this numerical invariant, we can obtain some information, important information about the structure of tensor product modules. I do not have time, but I finish this talk by stating the result which relates this numerical invariant with this Keller Scherotzke's theorem. So this is due to myself. So we can consider the for order for R matrix for fundamental representations. And we want to compute this number. And by using geometric technique, we can prove that this number is actually equal to dxy. So dxy is so this is by definition. So this is the dimension of x1 in derived category between corresponding indecomposable modules of object. So this theorem, so in particular, this theorem says that so if there is no extension for the corresponding indecomposable representation, then sorry, let me try to write this as a corollary. So if x1 is equal to 0 for corresponding indecomposable object, then we get to the commutativity of corresponding fundamental representations. And this is equivalence. This condition is equivalence for this condition. And so tomorrow I will explain how to prove this theorem by using geometry of quiver varieties. Okay, thank you very much for your attention.